So in this section of chapter 13, I want to talk a little bit about the orbitals and putting them in the context of some examples. And we'll be both looking at hybridization theory and MO theory as we go through these different examples. So the first example that I want to look at is going to be the example of ethane. Ethane's formula is C2H6. So with this, we have CH3, and that is bound to another CH3. So we have a nice alkane that we were talking about, carbon-carbon single bonds. What we're going to be looking at with this is all of those central atoms, which for us is carbon, all of those central atoms, things bound to more than one other atom, they're going to be hybridized, and we want to treat them as such. So one of the things that we want to be able to draw is we want to be able to draw all the orbitals associated with the molecule in terms of hybridization theory. We want to be able to draw the hybrid orbitals and the unhybridized orbitals, and then how they're going to interact or overlap in order to form our molecule. So if we look at ethane and we look at each of those carbon atoms, each of those carbon atoms is tetrahedral in nature, which means that they are all sp3 hybridized. If we were to actually draw out our Lewis structure, hopefully you would be able to see that each one of those carbons is tetrahedral, 109.5 degree bond angles. So now I want to take that structure and I want to put it into the context of my hybridization theory, my hybrid orbitals. So if I look at the carbon atom, the first carbon atom that I see, it's going to have 4 sp3 hybrid orbitals. So again, remember, with these, they're going to take that tetrahedral nature. So I'll have 2 in the plane, I'll have 1 pointing out at you, and I'll have 1 going back behind the plane of the screen. 3 of those sp3 hybrid orbitals are going to be bound to hydrogen. Hydrogen is only going to have the s orbital. So we denote hydrogen by being that sphere, since we're only dealing with the s orbital for hydrogen. That 4th sp3 hybridized orbital on carbon is going to be overlapping with another sp3 hybridized atom on the other carbon atom. So this is where valence bond theory comes into play, and that we have these overlap of orbitals. So when I get ready to put in my second carbon atom and its 4 sp3 hybridized orbitals, I need to make sure that I see that overlap of 2 of those orbitals to make that carbon-carbon single bond. We can then go ahead and fill in our hydrogens on that other carbon atom as well. So then one of the things that we wanted to note is we wanted to note the types of overlap that we're going to see. So all of the overlaps between carbon and hydrogen are what we call a sigma sp3s overlap. They're sigma overlaps because we see the electron density directly between the 2 nuclei. It's directly on that internuclear axis that we talked about previously. So all of the overlaps that we see in this structure between the carbon and the hydrogens would all be considered sigma sp3s overlaps. The overlap that we see between the 2 carbon atoms is also going to be a sigma. It's directly in between the 2 nuclei, but this would be a sigma sp3 overlap. So we're really defining the 2 types of orbitals that are overlapping as we talk about these types of orbitals. So one of the things that you want to be able to do for me is you want to be able to draw in our hybridization theory into our molecules and start denoting what types of orbitals are overlapping in order to actually make our molecule. So then the next thing we want to be able to do is we want to be able to put this into the context of our MO theory as well. So each pair of atomic orbitals that overlaps is going to follow our MO theory. So remember, if we have 2 atomic orbitals that are overlapping, that means I'm going to get out 2 molecular orbitals. And remember, each one of these molecular orbitals are different. They are not going to be degenerate. I'm going to have a bonding molecular orbital, and I'm going to have one of them be an anti-bonding molecular orbital. So my goal now is to take all of this bonding information and put it into the context of my MO theory as well. So if we actually look at the number of bonds that we have in our structure, we're going to go through and we're actually going to count them. So I'm just going to kind of try and denote them a little bit as we get ready to count them. I'll have 1, 2, 3, 4, 5, 6, 7. I have 7 pairs of atomic orbitals that are going to overlap, which means I have to multiply that by 2 because each one of those overlaps represents 2 atomic orbitals, one coming from each of the atoms, which means I have a total of 14 atomic orbitals that we're going to be putting in. So I'm going to look at an MO diagram, and I'm going to call it a simplified MO diagram because I'm not going to draw out all of the atomic orbitals, and I'm not going to draw out all of the molecular orbitals because there are so many. So we just got done counting, and we said that we were going to be combining a total of 14 atomic orbitals. We had 7 bonds. Each bond comes from an overlap of 2 orbitals, which means I have 14 atomic orbitals, and we're just not going to draw them all out. So we're going to simplify our notation a little bit. So I'm just going to write that we have 14 atomic orbitals that we're putting in. So since I have 14 atomic orbitals I'm putting in, it means I have to get out 14 molecular orbitals. But remember, they're split evenly. Half of them will be bonding, half of them will be anti-bonding. And remember, the bonding are going to be lower in energy than my anti-bonding. So if I actually look at my diagram, that means I'm going to have 7 bonding sigma molecular orbitals, and I'm going to have 7 anti-bonding sigma molecular orbitals that are going to be higher in energy. So this is our shorthand or simplified MO diagram. So now I want to be able to fill this in with electrons. And if we do our electron count, we have a total of 6 hydrogens at 1 electron apiece. I have 2 carbon atoms at 4 electrons apiece, which means I should get to a total of 14 total valence electrons. So I want to be able to decide where's my HOMO and where's my LUMO. So we want to be able to put the electrons into our molecular orbitals. And remember, each one of our molecular orbitals holds 2 electrons, which means my 7 sigma bonding molecular orbitals can hold 14 electrons. So all of these are going to be filled with 14 electrons, which means all of my anti-bonding molecular orbitals are going to be empty. I don't have any extra electrons to put in the higher energy state or the anti-bonding state, which means that these will be my HOMO, or one of them would end up being my HOMO, and up here one of them would end up being my LUMO. The next example that I want to look at is going to be an example of ethene. The formula for ethene is C2H4. So if we actually look at the structure, we now have a double bond between the 2 carbon atoms. So we have a nice trigonal planar shape for our carbon atom because we only have 3 electron domains around the carbon atom itself. So once again, since it's got that trigonal planar shape, these are going to be sp2 hybridized carbon atoms, and each carbon atom will contain 1 unhybridized p orbital. So now let's look at this in the context of our hybridization theory and our drawing out all of our hybrid orbitals. So I'm going to take and I'm going to draw my carbon atom, and I have 3 sp2 hybridized orbitals. The way that I'm going to draw them is they're all equivalent. They have that 120 degrees between them, but I'm going to draw them so that they are parallel to the floor, which means I've got one in the plane, I've got one pointing back behind you, and I've got one pointing out at you, instead of making them in the plane of the paper, and you'll see why here shortly. It wouldn't have been wrong to do it the other way. But then now 2 of these hybrid orbitals do have the hydrogens on them, so I go ahead and draw those in. And then that third sp2 hybrid orbital is going to be overlapping with the other carbon atom in terms of the sp2 hybrid orbitals. And they still have to have that same planar shape, so I'm going to go ahead and draw those in the same planar shape as well. Again, parallel to the floor. So one is coming out at you, one is going back behind the screen of the board. So these are all my hybrid orbitals. But remember, the sharing of orbitals can only be 2 electrons. So right now I only have 2 electrons being shared between those 2 carbon atoms. And if you look back to my double bond, there are now going to be 4 electrons shared between them. So what we have to look at with this is how are those 2 carbon atoms sharing that extra pair of electrons? And this is where that unhybridized orbital is going to come into play. So each one of those carbon atoms has that one unhybridized p orbital. And I'm going to put this now in the plane of my paper, so it's going to be on that x-axis. One lobe will be shaded, one lobe will not be shaded because it is going to be my unhybridized p orbital. And each one of those carbons has one of those unhybridized p orbitals. And what we're going to see is it's going to be these unhybridized p orbitals that are also going to overlap, and they are going to share electrons as well. And this is how we can put that second pair of electron density in between those 2 carbon atoms with these unhybridized p orbitals. Since the overlap is no longer on the internuclear axis, so hopefully you've been paying attention, that overlap is above and below that internuclear axis, this is what we refer to as a pi bond. So it's no longer a sigma bond that we would be looking at. This is now what we would refer to as a pi bond. The overlap would be what we call above and below that internuclear axis. So if we actually then get ready to label all of our interactions, all the interactions between the carbons and the hydrogens is going to be a sigma sp2 s overlap, and that would work for all 4 of those hydrogens. The overlap between the 2 carbon atoms would again be a sigma sp2 sp2, and then the p overlap is what we would call the pi bond. So we would just denote that as a pi bond. It's a overlap above and below the internuclear axis versus being a sigma overlap. And it can only come from those unhybridized p orbitals. So now we want to take this once again and we want to put it into the context of our MO theory. But one of the problems that we're now going to have is we have another type of bonding that we have to concern ourselves with. And it's going to be that p overlap, that pi bond that we have. So when we actually look at our MO diagram for the pi bonds and for our p orbitals, I just want to quickly look at what that's going to look like for our MOs. So our atomic orbitals this time are no longer going to be spherical. They're no longer going to have that direct overlap. We're going to be looking at those p orbitals. So there are my 2 atomic orbitals that are p in nature. So one side would be shaded, one side would not be shaded. Again, the middle is going to be my molecular orbitals. One of them is going to be lower in energy, one of them is going to be higher in energy. But when we get ready to do the overlap for my 2 nuclei, what we're going to see is that that overlap is going to be above and below the internuclear axis. So this is my pi molecular orbital. Notice it is still a bonding pi molecular orbital because the electron density is still overlapping. We still see electron density between the nuclei. It's just not on the internuclear axis. It's above it and it's below it. So this would be our bonding pi molecular orbital coming from those p orbitals. The anti-bonding molecular orbital, our electron density is going to be outside of the 2 nuclei. So this would be our pi anti-bonding molecular orbital. You'll notice that once again there's a nice node, no electron density, in between the 2 nuclei. So because we have this extra type of bonding in our structure, this pi bonding in our structure, we still have to account for that in our MO diagram as well. So we're going to start looking at not only having sigma molecular orbitals, but we're also going to have these pi molecular orbitals as well. So let's take a look at what that's going to look like in terms of our simplified MO diagram. for ethane. So again, let's go over to our diagram and let's count all of the atomic orbitals that we actually have here. So we would have 1, 2, 3, 4 from all the overlaps between our carbons and our hydrogens. We then have 5 in between our 2 carbons for the sigma bond, and then we have 6 with the pi overlap as well. So what we see here is that we have a total of 6 bonds. So remember, each bond has to have a total of 2 orbitals, which means I have 12 atomic orbitals that I am looking at in my structure. So one more time, remember we have a total of 6 bonds that we are looking at, and each bond has to come from 2 orbitals, 1 from each atom, which gives me a total of 12 atomic orbitals within my structure. So remember, we do have to split these evenly. Half of them will be bonding, half of them will be anti-bonding. But what we have to recognize with this structure is that they are all not going to be sigma. If we actually look at this, we only had 5 that were going to be our sigma bonding molecular orbitals, and those are the ones that were drawn in black. I then have 1 that is going to be my pi molecular orbital. So then we have the exact opposite. I would have 5 that would be our sigma anti-bonding molecular orbital, and I would have 1 that would be our pi anti-bonding molecular orbital as well. So notice the orientation. If we actually look at this, we have sigma bonding molecular orbitals being lower in energy than the pi bonding molecular orbitals. But if we reverse it when we look at the anti-bonding molecular orbitals, the sigma anti-bonding molecular orbitals are typically higher in energy than the pi anti-bonding molecular orbitals. So this is one of the orientations that you do want to watch for in terms of the energy levels, because sigma and pi do not have the same energy. They are not degenerate. Sigma bonding is typically lower in energy than pi bonding. Sigma anti-bonding is typically higher in energy than the pi anti-bonding orbitals. So now let's fill in some electrons so we can determine what is our HOMO and what is our LUMO. So if we do our electron count, we have a total of 12 electrons to put into our structure. So in our 5 sigma bondings, it's going to be filled with 10 electrons, and then this is going to be filled, our pi, with 2 electrons. Remember, 2 electrons in each orbital. So that accounts for our 12 electrons. So that means all of our anti-bonding are going to be empty. There are not going to be any electrons in that high energy anti-bonding state. So when we get ready to define our HOMO and our LUMO, the pi bonding is going to be our HOMO. It is the highest occupied molecular orbital. The pi anti-bonding is going to be our LUMO. It is the lowest unoccupied molecular orbital. So one of the things that you want to remember is anytime we have this double bond, so the double bond itself, we are going to have 2 electrons in a sigma molecular orbital, and we will have 2 electrons in a pi molecular orbital. And that is what really defines the double bond for us. 2 on the direct overlap, so 2 in a sigma type overlap, and we will have 1 in a pi type overlap. So the next example that I want to look at is going to be our example of formaldehyde. Our formula for formaldehyde is going to be CH2O. So if we actually get ready to draw out this structure, we're going to see a double bond between carbon and oxygen. Carbon is going to have 2 hydrogens on it, and then that oxygen is going to have 2 lone pairs associated with it. So I really want to put this example in to kind of focus on those lone pairs and where those lone pair of electrons are. So each one of the carbons and the oxygens are going to be sp2 hybridized. They have 3 electron areas around them, which means they have that nice trigonal planar shape. So my carbon is going to look just like it did previously. And I'm going to draw it in that same type of format where those sp2 hybrid orbitals are going to be parallel to the floor. And this time it's going to be overlapping with an oxygen. Again, that oxygen is going to be sp2 hybridized as well. The only difference is in these hybrid orbitals for oxygen, we're going to have lone pair of electrons. So we'll put in those two pairs of electrons in those hybridized orbitals. Each one of those atoms is still going to have that one unhybridized p orbital. And again, that is what is going to overlap to give us that second bond between our two atoms. So that those extra 2 electrons to give us a total of 4 electrons shared between those two atoms. So remember, that is that p orbital that has 2 lobes. One lobe is shaded, one lobe is not shaded. So if we look at this in the context of our describing our bonds, all of our bonds between carbon and oxygen are going to be sigma sp2s. The bond between the carbon and the oxygen would be a sigma sp2 sp2. And then we would also have the pi bond between the carbon and the oxygen as well. So really the only thing that changed here is that we can put lone pair of electrons in those hybrid orbitals, and that's where they would show up. They would typically show up in those hybrid orbitals. Those are our non-bonding pairs. What's going to change slightly is going to be how we actually look at our simplified MO diagram, because now those aren't going to be bonds there, but they are still going to be orbitals for us. So these non-bonding pairs form what we call non-bonding molecular orbitals. Those non-bonding molecular orbitals, they have the same energy as what the atomic orbitals do, but they're not going to be used in any bonding, which is really what the key is they're not there for bonding. They're what we call non-bonding molecular orbitals, and they have the same energy as what atomic orbitals do. So if we actually go through and we build out our simplified MO diagram once again for this structure, if we look at all the bonds that we have 2 bonds between carbon and hydrogen. We have 1 sigma bond between the carbon and the oxygen. We have 1 pi bond as well between them. And then we have our other, and each one of those would be doubled. So that would give us a total of 8 in terms of bonding. And then we have our 2 individual orbitals as well, which gives us a total of 10 atomic orbitals. So please notice the difference between our formaldehyde example with the lone pairs and the ethene example that did not have any lone pairs. We're now down to 10 atomic orbitals. But we have to be careful the way that we split these because we do have our 2 non-bonding molecular orbitals. And I'm just going to fill those in first because they have the same energy as what the atomic orbitals would have. So I'm going to draw them right on the same line, which means I really only have 8 atomic orbitals that are going to go into forming the anti-bonding and the bonding because we have 2 orbitals coming together. So with that, what that means is I'm going to have 3 sigma bonding molecular orbital. I'm going to have 1 pi bonding molecular orbital. I'm then going to have 1 pi anti-bonding molecular orbital and 3 sigma anti-bonding molecular orbitals. So you do want to be very, very careful when those lone pairs come into play. They do show up in our MO diagrams, but they show up as non-bonding electron or non-bonding MOs. And then we split the rest of those into our typical bonding and non-bonding. So if we count up the total number of electrons, I still have 12 total electrons that I need to fit in. So with this, my 3 sigma bonding are filled with 6 electrons. My 1 pi bonding is going to be filled with 2 electrons, which gets me up to 8. My non-bonding is then going to be filled with 4 electrons as well. And then all of my anti-bonding molecular orbitals will be empty. So now when we get ready to define the HOMO and the LUMO, the HOMO is now going to be my non-bonding molecular orbitals Well, my LUMO is still the pi anti-bonding molecular orbitals. So you do want to be careful with those lone pairs. They will show up in our hybridization theory, but we can also use them in our MO diagrams as well as non-bonding molecular orbitals. The last example that I want to look at is going to be ethine. The formula for ethine is C2H2. With ethine, this is a triple bond between the two carbon atoms. So this is now going to be sp hybridized. It forms that nice linear shape, so it will be sp hybridized, which means that it has two unhybridized p orbitals that we're going to be looking at in our hybrid orbital diagram. So this time I'm going to draw my carbons. There's one sp, here's my second sp. Again, they are going to be nice and linear in shape for me. The one sp orbital is what's going to be overlapping with my hydrogen bond. The other sp is what's going to overlap the other carbon atom as well. So this is what my hybridization theory looks like in terms of all the hybrid orbitals that we have. But now I have to fill in those unhybridized orbitals, and it's going to be those unhybridized orbitals that's going to account for the second pair and the third pair of electrons shared between the two carbon atoms. So with this, I have my two unhybridized p orbitals. I'm going to go ahead and put one of them in that x-axis, and I'm going to shade one lobe on each of them, and this is where we will see the overlap for the second pair of electrons shared between the two carbon atoms. The second unhybridized p orbital is going to go out of the plane and back behind the plane, and again I'm going to shade in one of those lobes on each one. It is going to be the overlap between that p orbital that is going to account for the third pair of electrons that is shared between the two carbon atoms. So if we actually get ready then to denote all the types of bonding that we have between the carbon and the hydrogen, we have a sigma sps bond. Between the two carbon atoms, we have a sigma sp bond. And then we have two pi orbitals two pi bonds between the two carbon atoms as well. One from each of the unhybridized p orbitals associated with them. But please notice that the p orbitals have to be in different planes. I have one on the x or y plane, and I have one in the z plane. They cannot be in the same plane. They have to be on opposite planes, because remember, those orbitals all have to be on different planes around our central atom. So this is what our hybrid orbital diagram looks like for ethine. We can then look at our simplified MO diagram as well for ethine. With this, we're going to be putting in a total of 10 atomic orbitals. Please make sure that you can still count out how we got to that value of 10 atomic orbitals. When we get ready to split these, we are going to have 3 sigma bonding molecular orbitals and 2 pi bonding molecular orbitals. I will then have 2 pi anti-bonding molecular orbitals, and I will have 3 anti-bonding sigma molecular orbitals as well. So please make sure you know how to get to that count. From here, we're going to fill in all the electrons, and we're going to have a total of 10 electrons in our structure. So my sigma bonding molecular orbitals will be filled with 6 electrons. My pi bonding molecular orbitals will be filled with 4 electrons, and that is all the electrons I have to put into my structure. So it means all of my anti-bonding molecular orbitals will be empty. To then define the HOMO and the LUMO, the pi bonding molecular orbitals will be my HOMO. The pi anti-bonding molecular orbitals will be my LUMO. Those 2 pi's, the pi bonding are degenerate, the 2 pi anti-bonding are degenerate. So once again, we would not say which one of them is the HOMO, but that would be our HOMO level. So please make sure with these simplified diagrams that you can draw all of them. You can do all the accounts to get to your MOs. and that you can also draw out all of your hybridization and unhybridized orbitals in our structure as well.